Okay, first of all, I would like to thank the organizing committee for this wonderful event. Today I'm going to tell you a little bit about my research that I conducted at Bilkent University in Turkey, then during my PhD here at Northwestern University, and finally I'll tell you a little bit about what I'm up to at Harvard University now. So I was born and raised in Eskişehir. Although it's a wonderful city, during winter time when I was a kid, the whole city was turning into black because of the extensive use of coal. So now things are changing a little bit with the use of natural gas and alternative sources, but this is still a global issue in terms of air pollution. So this picture is taken in Beijing last year, and everyone is trying to protect themselves and their kids to protect themselves from air pollution. And if you look into this data, which is collected at Hawaii, United States, the atmospheric carbon dioxide level in our atmosphere is increasing. And since 1960 to 2010, there was a constant increase in the carbon dioxide level, which is increasing the greenhouse gases in our atmosphere and increasing the temperature of the world. So lately, there has been a united effort from the delegates from different countries, and in the Paris climate talks, there are some decisions taken to reduce the carbon dioxide emissions. So my research theme so far was based on what we can do in terms of reducing our carbon emissions. At Bilkent University, I was focused on energy conservation. Instead of using incandescent light bulbs, we can move to light-emitting diodes, which are more efficient in terms of energy consumption. And then during my studies at Northwestern University, I was into renewable sources because we have the sunlight out there, which is always shining, although it's snowing today. But we can use that sunlight to create electricity. And there has been a lot of research on this. But lately, the main focus is how we can manipulate the light so that we can get better solar cells. And finally, my research at Harvard University is focused on using carbon dioxide and turning it into useful products, for example, ethanol and methanol, so that we can use them as fuels. Or we can think of carbon-neutral fuels. Instead of using carbon, what we can do is we can start with water and split it into molecules of hydrogen and oxygen. And recently, Toyota showed their hydrogen-powered car. So there are a lot of opportunities, but the main theme of my research has been finding chemistry-enabled tools so that we can fabricate these structures and understand the fundamentals. So I'll tell you a little bit about nanotechnology and how we can create these structures and how they are different than their bulk counterparts. For example, on the left, we are looking at cadmium and tellurium atoms, which came in the form of a quantum dot. They are very small, and they're in the size of 4 nanometers. And just to remind you, a nanometer is a billionth of a meter. So these are really small particles. And if we add a little bit more atoms around this, make this instead of 4 nanometers to 6 nanometers, we see a drastic change in the way that we see them with our eyes. So we have done a lot of research at Bilkent University to find different combinations of these quantum dots to create higher efficiency and higher quality white light emitting diodes. And some of our research work, especially with quantum dots and combination of polymers and quantum dots, have been highlighted from Nanotechnology and Journal of Materials Chemistry. Another particle of interest is the metal particles. For example, when we look at a gold coin, we see it as yellow. The color of gold is yellow to us. But things are a little bit different when we go into nanoscale. For example, here we are looking at gold nanoparticles, which are in the size of 15 nanometers. So the way that light is interacting with material is different in the nanoscale. That's why we are seeing them as red instead of yellow. And it's all related to how electrons are oscillating around these metal nanostructures. So one key question that I had before I moved to Northwestern University was, can we bring these metal structures and semiconductors together so that we can understand the fundamentals better in terms of creating better efficiency solar cells? And also, can we enhance the absorption of the semiconductors so that we can use metals in proximity of semiconductors? Because of the contrast, maybe you cannot see, but here we are addressing the electrical properties by suggesting that we can create core shell nanowires. And here we have metal structures all around the wire, which are absorbing the light and then transferring the energy into the semiconductor region so that we can have better efficiency devices. During the time that I started my PhD, the state of the art was creating nanowires in one-dimensional control. So here we are looking at a multi-segment nanowire, and the bright contrast corresponds to gold, and these are the darker ones are the nickel segments. And using electrochemistry, we can actually control this down to 5 nanometer resolution. We can create one-dimensional nanowires. But a nanowire has 2 dimensions, actually. The axial dimension, which we can control here, and also the radial dimension. To create core shell nanowires, we had to come up with ways to play with polymers and also the templates that we use to create these wires, so that with a dynamic approach, controlling the size of the template and making it smaller and bigger, and also putting some materials inside as polymers which have different chemical stabilities, we can create core shell structures and even more unique structures as these metal nanorings if we design everything in a perfect way. So this allowed us to bring the one-dimensional nanowire research into 2-dimension using electrochemistry. So we can even create structures which have semiconductors inside, which is wrapped by another semiconductor outside. So this serves as a photodetector in the nanoscale. And then we can even integrate metal structures, antennas, which will transfer the light. And these outperform the bulk counterparts. So with all of the knowledge that I gained at Northwestern University in terms of nanowire research and electrochemistry, now at Harvard University, we are making arrays of these wires in centimeter scale, so that we can turn these into useful devices to convert carbon dioxide into ethanol and methanol. Finally, I would like to say that although scientists are focused a lot in terms of finding alternative energy sources, we all need to be really careful in terms of conserving energy. So I'm saying go green, save energy, and save our future.